Alright, so section 5.4, part 1, we're going to be looking at exponential functions and their derivatives. So let's go ahead and get started with a couple of problems from pre-calc that I want to see if you remember how to do. So we want to solve this for x. So if I'm trying to bring something out of the exponent, then what I need to do is take a logarithm of both sides. Now, you could take any logarithm you want to, but I am doing a logarithm with a base of e, so I'm using the natural logarithm. And that's mainly because the base of this exponential is e. Alright, so this is what will allow me to bring the x plus 1 out of the exponent. So I have ln of 7. Remember, ln of 7 is just a number. You can plug that into your calculator and see what you get. So I'm going to bring the x plus 1 down, and I'm left with ln of e. Now, if you remember from pre-calc, ln of e is just equal to 1. So what I'm left with here now is ln of 7 equals x plus 1, because x plus 1 times 1 is just x plus 1. I want to get x by itself, so I'm going to subtract 1 to the other side, so negative 1 plus ln of 7 is my final answer. That's your exact answer. You could plug that into your calculator if you wanted to. But that is the exact answer. One thing you don't want to do is subtract the 1 over here and say it's ln of 6, or even, you could write x equals ln of 7 minus 1, but sometimes people will end up writing ln of 6, which is not the same thing. So I don't like writing it that way. I prefer writing it this way. But like I said, it's just a preference. Here is a logarithm. We want to solve this one for x. So ln of 2x minus 3 equals 5. If you remember from from pre-calc, you have a way of going from logarithmic to exponential form. I had a student tell me this was the way that he remembered this a long time ago. This was the method that he used. He called it the triangle of death. And that's because he hated logarithms, and this was what he did to help him remember this. So we do b raised to the power of x equals a. So this was his little triangle that he did. So b raised to the power of x equals a. So I'm going to use that same concept here. My base here for ln is e raised to this power, which is 5, equals all of this. So 2x minus 3. E to the 5th power is a number, again, that you could plug that into your calculator and get the decimal approximation for that. Whatever it is, doesn't matter. We want to get x by itself. So I'm going to add 3 over, so 3 plus e raised to the 5th power equals 2x, and then divide by 2 to get x equals 3 plus e to the 5th power divided by 2. That's your final answer. Again, you could plug that into your calculator to get an approximation if you want to, but I'm going to let that up to you if you want to do that. That's the exact answer right there. Alright, so welcome to the easiest derivative that you will do all year long. Let u be a differentiable function of x. If I'm trying to take the derivative of e to the x, it is e to the x. So if I take the derivative of e to the x, I get e to the x. Simple as that, okay? That is the only derivative that gives you itself other than 0. So there it is. The only other thing we need to be concerned with is if we're trying to take the derivative with respect to x, and e has an exponent that is in some other function, we got to take into consideration our chain rule. But we always recopy this first, and then we take the derivative after that. Okay, so like with this one up here, there is the derivative of x would be 1, so times 1. But obviously that doesn't change anything, so e to the x is the derivative. But if your exponent is something like sine x, you would write e to the sine x times cosine x. So let's do a couple of examples, and maybe it'll clear up anything for you here. So again, this exponent is something that is not just simply an x, it's a different function, so we're going to have to take the derivative and use chain rule here. So first of all we do is recopy. So e to the 2x minus 1 times the derivative of your exponent. So the exponent is 2x minus 1, and the derivative of that is just 2. So just to clean it up a little bit here, 2e raised to the 2x minus 1. Make sure the 2x minus 1 is all in the exponent. If you have trouble showing that with your handwriting, as I know my handwriting gets a little messy at times, maybe you want to throw some parentheses around that, but the 2x minus 1 needs to all be in your exponent. So there you go. One more of these. E raised to the negative 3 over x. So if you want to, like, off to the side, rewrite this like negative 3 over x, this is the same thing as negative 3x to the negative 1. That may help you do your derivative. But again, first thing we always do is recopy our exponential function. So e raised to the negative 3 over x times the derivative of the exponent, which I'm going to come back up here to this. Power rule says bring that out front. So 3, subtract the exponent by 1, so negative 2. So I'm left with 3x to the negative 2, which I will again clean up and write 3e to the negative 3 over x. All of this is over x squared. All right, now let's get into some application here. So find the relative extrema. If you remember from when we did this back in chapter 3, relative extrema is when we take the derivative and set it equal to 0. So let's do that. So the derivative, this requires product rule. I have one function, x, times another function, e to the x. So we got to do product rule here. So the derivative of the first is 1 times the second is e to the x plus the first function, which is x, times the derivative of the second. The derivative of e to the x is just e to the x. So we're going to set that equal to 0. So e to the x plus x e to the x equals 0. And we need to figure out where is this equal to 0. So first of all, let's factor out an e to the x. And I'm left with 1 plus x equals 0. So from this right here, 1 plus x equals 0. That tells me that I have a 0 at negative 1. But how about e to the x? What I want to know is, will this ever be equal to 0? And maybe to answer that, we should look at what the graph looks like. So the graph of e to the x has the point 0, 1, so it has that point there at 0, 1, follows along the x-axis on the negative side, goes through the point, and then up. So I don't know if that's a graph that you guys have seen before from pre-calc or not, but that's what the e to the x function looks like. Now, although this over here gets very, 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 very close to 0, it will never be equal to 0. So this will not get us a 0, therefore my only answer is negative 1. And one more example for you here, because I know it's been a while since we did the optimization problems, and you're probably missing them right about now, so I wanted to throw one of these in here. So let's look at what we're talking about here. Let me scroll up so we can put this on here. So let's look at what we're trying to find. So like I had just said there, we know that all exponential functions pass through the point 0, 1. Now, if we think about this when we plug a negative number in here, first of all, if we plug any number into x squared, it's positive, and then putting the negative out front means it's negative. So anything raised to any number raised to a negative power will give you a fraction. So if this is 1 right here, all of these values will be fractions. So it's going to kind of look like this on both sides, okay? And it's going to be a mirror image. Mine does not really look like a mirror image, but it will be a mirror image there. So what we're trying to do here is find the maximum area of a rectangle that has 2 points, 2 of the vertices on the x-axis, so like 2 points right here, and then 2 points on the graph, so like 2 points right here. So we're trying to find the area of this rectangle. So if you remember back to optimization problems, we have a primary equation that helps us solve the problem, which is the maximum area, so length times width or base times height, whatever you want to look at there. And then we have a secondary equation that will be plugged in later. So if I'm looking at my length here, okay, my length, let's say this is my length, well, this value going from here 0 to this vertex is, we don't know what it is, but if we're going to generalize this, we're just going to say this is x. And then this over here would also be x, but it would be in the opposite direction. Okay, so my length is 2x. Okay, and again, that's just this value right here. This is my length. Also this value right here. My width then, okay, the width would be this value right here. Okay, this piece of the rectangle right here, which is just your y coordinate. So that's going to be y. Now, I don't want to take the derivative of this. I'm going to plug this in because now it gives me something that's all in terms of x, and this would be your secondary equation that's going to be plugged in here to help me solve my primary equation. So let's go ahead and do that. So area equals 2x times e to the negative x squared. And if you can remember back to optimization problems, what we do after this is, because optimization is just finding a maximum or a minimum value, so what we do is we take the derivative and set it equal to 0, and that will give us our value for x, and then we're going to bring it back and plug it in here to this function right here to actually solve the question, answer the question, what is the maximum area? Alright, so let's do what I just said there. Take the derivative, a prime. So again, product rule, we have the first and second function here. So product rule says the derivative of the first, which is 2, times the second, e to the negative x squared, plus the first, which is 2x, times the derivative of the second, which again we recopy, and then take the derivative of your exponent, which is negative 2x. Now we're going to set this, well, let's clean it up first. A prime is 2e to the x squared, negative x squared, minus 4x squared, e to the negative x squared. We're going to set this equal to 0. So before I set that equal to 0, I'm going to factor some stuff out. So they both have a 2e to the negative x squared. What's left? Well, in the first term here, I'm left with a 1, minus, in the second term here, I'm left with a 2x squared. Now, what we talked about in that last problem is that this right here will never be equal to 0. Exponential functions will never be equal to 0. So that means we just have to set this equal to 0. So 1 minus 2x squared equals 0. Where does that happen? So x squared, subtract 1, divide by negative 2, you get 1/2. And then take the square root, we get plus or minus the square root of 1/2. So what that means is that this vertex over here was at the square root of 1/2, and this one over here was at the negative square root of 1/2. But anyway, to get our final answer, what we will do now is come back down here to this function and plug that in. So we got 2 times the square root of 1/2 times e to the negative square root of 1/2 squared. And that you're just going to plug into your calculator, plug this right here, the stuff in blue, plug that into your calculator and get your decimal approximation. Again, it should be a small area because, I mean, square root of 1/2 is a pretty small number. So, you know, that was your x coordinate there. So anyway, there you go. That's the exact answer right there, and you can plug that into your calculator to get a decimal approximation. All right, so here's some problems for you to try. Let me know if you have any questions, and we will finish up doing some exponential stuff in the 542 notes. So let me know if you have any questions on this stuff.